Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we're doing a really important deep dive. The topic is nuclear energy from Unit 13, Nuclei. Our goal is simple, to make this topic so clear and exam-safe that you remember it for life. Okay, so to get started, let me ask a simple question. How is it that the sun has been, producing these massive amounts of light and heat for billions of years without ever running out of fuel? It can't be like burning coal, right?
That's a great question, because if it was just coal, given the sun's mass, it would have burned out in just a few thousand years.
Exactly. A few thousand years.
Yeah.
But we know it's been going for 4.5 billion years. So something totally different is happening inside it. And here's where it gets really mind-boggling. In a normal chemical reaction, like burning coal, the energy comes from the electrons, and the energies are tiny in the range of electron volts, or eV. But when you go inside the nucleus, the forces are millions of times stronger. So the energy released in a nuclear reaction is also millions of times higher. We're talking mega electron volts, Maeve.
Millions of times. Can you give a comparison? Like, what does that actually look like?
Absolutely. And this is the surprising fact. If you take just 1 kilogram of uranium and cause fission, it generates about 10 to the power of 14 joules of energy.
Okay, 10 to the 14.
Now compare that to burning 1 kilogram of coal. That gives you only about 10 to the power of 7 joules.
So that's a factor of 10 million. A million times more energy from the same 1 kilogram.
10 million times. So we have to understand where this phenomenal energy is coming from. The zero-level core idea is actually quite beautiful. Nuclear energy simply comes from the nucleus rearranging itself to become more stable.
More stable?
Yes, more tightly bound. And in that process, a tiny, tiny amount of its mass just vanishes. It converts directly into that enormous energy, following Einstein's famous relation.
Equals mc squared.
E equals mc squared.
Yeah.
That tiny bit of missing mass, the mass defect, becomes the energy.
So it's not creating energy, it's just converting mass into it, and stability is the main driver here.
Precisely. Stability is the key to everything. To understand this, let's use our main analogy for today, the binding energy landscape. I want you to picture a graph that looks like a sort of mountain valley. The vertical axis, how high up you are, is the binding energy per nucleon. Let's call it EBN.
And a nucleon is just a proton or a neutron, correct?
Correct. So this EBN value, it's a direct measure of how stable a nucleus is. The higher the binding energy per nucleon, the more stable the nucleus. And when you plot this against the mass number, the total number of nucleons, you see a curve that rises, hits a peak, and then slowly drops. That peak, the most stable point, is around mass number 56.
Which is iron 56, so that's the most stable element in the universe.
It's the nuclear dead end.
Yeah.
In a good way.
Yeah.
It has the highest EBN, about 8.75 MeV-E. It's the goal. Any nucleus that moves towards iron 56 on this graph has to release energy.
Okay, so how does that work?
Well, look at the graph. The light nuclei, like hydrogen, are on the left slope, way down. To get more stable, they have to combine and climb up the slope. That process is fusion.
Combining to get more stable. Got it.
And the really heavy nuclei, like uranium, are on the other side, on the right slope. They're past the peak. For them to get more stable, they have to split apart and move back towards the center. That's fission.
So both are trying to get to that stable peak of iron, one by combining, the other by splitting.
Exactly. Just visualize it. A heavy uranium nucleus rolling down the right slope by splitting, and light hydrogen nuclei climbing up the left slope by fusing. Both processes result in products that are more stable, and that difference in stability is released as massive energy.
That analogy helps a lot. So just to confirm, energy is released because the end products have a higher binding energy per nucleon, which means a little bit of mass was lost.
That is the one-line summary you need to remember.
Perfect. Now that we have the picture, let's get the formal exam-ready language right. Let's see how NSERT defines these processes. Could you read the exact definition for us?
Of course, I have it here. For fission, NSERT says it is when a heavy nucleus decays into 2 or more intermediate mass fragments.
Okay, and for fusion?
For fusion, it says light nuclei fuse into a heavier nucleus. And it adds that energy is released when less tightly bound nuclei transform to nuclei with greater binding energy. That last line is the key. It connects directly back to our stability curve. So let's break down the actual mechanism step by step. Let's start with fission. We use uranium-235. It's a heavy nucleus with a binding energy per nucleon of about 7.6 MeV. When it absorbs a neutron, it splits into 2 smaller fragments, like, say, barium and krypton.
And barium and krypton are closer to iron on the curve, so they must be more stable.
They are. Their binding energy per nucleon is much higher, around 8.5 MeV.
So you're going from 7.6 MeV per particle up to 8.5. That's a gain of 0.9 MeV for every single nucleon.
Exactly. Now, do the maths. You have roughly 240 nucleons in uranium. So 240 times that 0.9 MeV gain, that gives you about 216 MeV of energy from a single fission event.
A single atom. That's incredible.
And this energy comes out as kinetic energy of the fragments. They fly apart, crash into things, and generate immense heat. But here's the most important part, the chain reaction.
Ah, yeah.
When U-235 splits, it doesn't just release energy, it also spits out 2 or 3 new neutrons.
And those neutrons can then hit other uranium atoms.
And cause them to split, releasing more neutrons, which hit more atoms. It's a domino effect. Uncontrolled, that's an atomic bomb.
So in a power plant, you have to control it somehow. How is that done?
Great question. It's all about managing the number of neutrons. We use something called the neutron multiplication factor, K. If K is greater than 1, the reaction explodes.
The bomb.
Yes. If K is less than 1, it fizzles out. In a reactor, the entire job is to keep K perfectly equal to 1. We call this a critical state.
And how do you keep it at exactly 1?
We use control rods made of materials like cadmium or boron. These materials are like sponges for neutrons. We can push them into the reactor core to soak up excess neutrons and slow things down, or pull them out to speed things up. It's a very fine balancing act. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's switch gears to nuclear fusion. This is the process that powers the sun. Here we are combining very light nuclei, for example in the sun, 4 protons, which are just hydrogen nuclei.
Combined to form a helium nucleus?
Exactly, a helium-4 nucleus. And helium-4 is much, much more tightly bound than 4 separate protons. In the sun's proton cycle, the net result is that 4 hydrogens become 1 helium, releasing a massive 26.7 MeV of energy.
Again, moving to a more stable state.
Always. Let's do a quick worked example with a reaction we're trying to achieve on Earth, the deuterium-tritium or DT reaction.
Okay.
The reaction is deuterium plus tritium gives you helium-4 plus a neutron plus energy, which we call Q.
Right.
So let's look at the masses. We need the precise values in atomic mass units, or U. Deuterium has a mass of 2.014102. Tritium is 3.016049 U. Can you add those up?
Let's see. That comes to 5.0002 or 151 U. That's the mass of the reactants.
Now for the products, helium-4 is 4.0802603 U, and the neutron is 1.008665 U.
Hey, that's less than what we started with.
Exactly. The product mass is lower. That's the mass defect. What's the difference?
It's 5.030151 minus 5.011268, which is 0.018883 U.
And that tiny missing mass, 0.018883 U, is what becomes energy Q. We know that 1 U is equivalent to 931.5 MeV. So we just multiply.
So 0.018883 times 931.5 MeV.
And you get about 17.6 MeV. A huge energy release, all proven by that tiny difference in mass. It's a direct confirmation of E equals mc squared. And just to quickly connect this, those fragments from fission, like barium, are often unstable themselves. They then go through a series of beta decays to reach a final stable state. This shows the link to the next topic, radioactivity. Okay, now for a very important section. Let's talk about the silent killers, the misconceptions that can cost you Mars. Misconception number 1, the wrong idea is that a nuclear power plant can explode like an atomic bomb.
Right, because they both use fission, so it seems logical.
It seems logical, but it's physically impossible. The correct idea is all about enrichment. The fuel in a reactor is only 3 to 5% U-235. It's too dilute. For a bomb, you need over 90% enrichment to get that runaway chain reaction.
So the fuel itself isn't pure enough for a nuclear detonation. Accidents like Chernobyl were steam or chemical explosions, not nuclear ones.
Precisely. It can melt down, but it cannot detonate like a weapon. That's a key distinction. Okay, misconception number 2, the wrong idea. All nuclear reactions release energy. You split something or fuse something, and you get energy.
But that can't be true because of the curve, right?
Exactly. The correct idea is that you only get energy out, an exothermic reaction, if you move towards the iron 56 peak. If you try to fuse 2 iron nuclei together, you're moving away from the peak. That requires energy input. It's endothermic.
So you always have to ask, are the products more stable than the reactants? Only then is energy released.
Perfect. And the last one about fusion, misconception 3. Fusion must be easy because it releases so much energy.
But you hear about how difficult it is to build fusion reactors.
Because it is incredibly difficult. The correct idea is that you're trying to force two positively charged nuclei together.
And they repel each other, the Coulomb force.
An enormous repulsive force. To overcome that barrier, you have to heat the fuel to insane temperatures, something like 100 million Kelvin. Creating and containing a plasma that hot is one of the biggest scientific challenges ever. All right, time for some memory anchors to lock this in. Remember iron 56, that stability peak?
The nuclear dead end.
That's our catchy phrase. Iron 56, the nuclear dead end. Can't fuse it, can't fission it, can't extract energy from it. It's the ultimate point of stability. And for a physical gesture, try this. Use your hand in the air to trace the binding energy curve. A steep rise on the left for fusion, a sharp peak in the middle for iron 56, and then a slow, gentle drop on the right for fission.
Oh, that's clever. The motion itself reminds you of where the energy comes from.
It's exactly. The movement towards the peak is what releases the energy. Let's wrap up with a 3-point summary, just the core exam-safe facts. Point 1. Nuclear energy comes in the mass defect. A tiny amount of mass is converted into binding energy, according to E=mc². This happens when nuclei rearrange to move toward maximum stability, which is iron 56. Point 2. Fission splits heavy nuclei, like uranium. Fusion combines light nuclei, like hydrogen. Both processes release energy because the final products have a higher binding energy per nucleon. And point 3. Fission in reactors is a controlled chain reaction where the multiplication factor K is kept at 1. Fusion powers the sun, and on Earth requires extreme temperatures around 100 million Kelvin to overcome the Coulomb barrier. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSAM, right?
Yes, ProfSam.com. Thank you for tuning in to this deep dive.